This study aimed to develop and validate a two-dimensional homogenized model, H2D, that can accurately predict the tensile and bending responses of a double-wall corrugated board. The proposed method simplifies the 5-layer, 3-dimensional structure into an equivalent 2-dimensional plate, significantly reducing geometric and computational complexity while maintaining high predictive accuracy. In this study, we investigated 3 paper types used in the cardboard's construction: KRAFT LINER, KL, for the outer layers, DUOSAICA, DS, for the fluting, and AUSTRO LINER, AL, for the intermediate layer. A comprehensive experimental campaign was conducted to characterize these constituents. This included measuring physical properties like density, observing the fibrous microstructure via scanning electron microscopy, SEM, and performing X-ray diffraction, XRD, analysis, which identified cellulose as the matrix with quartz as the primary mineral filler. Crucially, in-plane tensile tests according to ASTM D828 were performed in the machine direction, MD, cross direction, CD, and at 45 degrees. These tests quantify the material's strong orthotropic nature, providing the essential elastic moduli, Poisson's ratios, and shear moduli required as input for the homogenization process. The core of the work is the analytical homogenization model, which integrates classical lamination theory with sandwich structure theory. The complex corrugated geometry of the double-wall board is addressed by analyzing a representative volume element. This RVE is first sliced and integrated through its thickness, with the stiffness of the inclined fluting layers transformed to the global coordinate system based on their local angle. A second homogenization step is then performed by averaging the stillness contributions over one full period of the corrugation pattern. This process yields the equivalent stiffness matrices for the 2D plate, the membrane, membrane bending coupling, and bending matrices, which fully describe the global orthotropic behavior. The predictive capability of the H2D model was rigorously validated by comparing its results against a high-fidelity 3D finite element model, ANSYS 3D, of the corrugated board. Both models were subjected to simulated tensile and bending loads in the MD and CD directions. The comparison of displacements showed an excellent correlation, with discrepancies systematically below 2% for all loading configurations. The H2D model achieved this accuracy while using a fraction of the computational elements and nodes required by the full 3D model. This study successfully demonstrates that the proposed analytical homogenization H2D model, informed by detailed experimental characterization of the constituent paper layers, provides a robust and computationally efficient tool for predicting the global tensile and bending stiffness of double-wall corrugated cardboard. Its high accuracy, with errors below 2%, and reduced complexity make it a reliable and practical alternative to full 3D modeling for the structural analysis and design optimization of corrugated packaging systems, particularly for applications dominated by axial and flexural loads.